All right. Look, a fun font. Doesn't that make the notes so much better? You're like, oh, this is a good font. This font is, if you use it for business purposes, like in an individual classroom, it's called peony. Like a flower. It's not very floric. Floral, thank you. That's like, that was just like my elementary nightmare. I say something and the whole class is like, rude. All right. A normal distribution is a continuous, symmetric, bell-shaped distribution of a variable. The properties of a normal distribution are, it is bell-shaped, as was previously stated. The mean, median, and mode are equal and are located in the center. Somebody remind me what the mean, median, and mode are. Yes?
The mean is all the numbers added up and divided by how many numbers there are.
Mm-hmm.
And then the median is the one like in the middle, in order. And then
the mode is, yes?
It's the number of the set.
Yeah, that repeats itself the most often. So what they're saying is one average and another average and the last average, because those are all different ways to calculate averages, right? All of the averages are exactly the same. Do you think this happens in real-world data very often?
No.
Not so much. Okay. Now, sometimes when we look at data, it's like an approximate bell curve where it's like, yeah, there's a lot in the middle. That kind of makes sense. If I was to group, in this class would not be a bell curve. A bell curve is kind of like saying that everybody's getting like C's. Lots and lots of people are getting C's. A few people get A's, a few people get F's. Does that make sense? That's generally not the case in an honors class. An honors class would be lots and lots of A's, very little F's. Does that make sense? Sometimes in our upper level classes, we have what we call a reverse bell curve, which means people either get A's or F's and nothing in between. That often happens. You have the people, and it's not an intelligence issue. It's this is really hard, I give up. Does that make sense in like an upper level class? Okay. So bell curves are supposed to represent specific types of data where you say there's a lot of people that fit the average. Does that make sense? So it's like right there in the middle, and in a class we would consider that to be like the C range. So we would say that the middle of a bell curve is like a 70%. That's like your average grade. Okay. A normal distribution curve is unimodal, which just means it has one mode, so there's only one grade that is repeated the most often. There's not two different grades. It's not like a bunch of people have 70s and a bunch of people have 75s. Like, it's like a bunch of people have 70s and that's it. That's like the average, okay? The curve is symmetric about the y-axis. So we could say that this right here in the middle, we could call that the y-axis. And the y-axis is actually where the mean is, the mean, median, mode. Those were all like the exact middle. Its shape is the same on both sides. The curve is continuous. There are no gaps and no holes. Do you guys remember what we say for continuous? Can trace it with your finger without picking up your finger. It's continuous. The curve never touches the x-axis. So the x-axis is over here. So theoretically, no matter how far the curve extends in either direction, it will never meet the axis, but will get increasingly close to it, which is the definition of an asymptote, is that your curve gets closer without, well, it could touch it, but not in this case. The total area, so if I was to shade all of this in, the total area would be one whole unit, 1.00 units. which means that we talk about this in terms of percentages. What percentage out of that whole you end up having. Okay, so whenever you look at a normal distribution, this does not represent all data. This is specifically if they tell you that it's a normal distribution, you have to see those words to begin with. So when we talk about it today, we're just going to assume all the distributions we talk about are normal. We're going to assume that. But to be able to use this, you have to know that the data is normal first. It doesn't make sense to apply this to all information because it doesn't always work, okay? So if it's normal, then this right here would be the 50th percentile, right? 50% on the left, 50% on the right. So there's 34% right here. We'll describe what that means in a second. 13.5% of the results are going to fit right here. 2.35% of the results fit there. And then 0.15% of the results fit up there. And it's symmetric, so we're going to fill in those same percentages on the other side. Okay. So if this was to fit classrooms, then we would say 50% of the class had less than a 70% and 50% of the class had greater than a 70%. That would freak out the honors kids, right? Like looking around the room, half of us have less than a 70. That's no good. That'd be like only the top 2.5% have A's. That's not even one person in this room. Maybe one, yeah. One. No, that is one person in this room, but you know what I'm saying? Like, whew, that's not very many A's. All right. Yeah, 0.15, 0.15. Yeah, notice that was less than a percent. 0.15. Okay. So I'm going to erase this real quick, this 50%. Okay. Go ahead and write. This is the Greek letter mu, like the sound, like kind of like the sound a cat makes. Mew, mew, mew. All right. It's like a U with a long tail in the front. It's like you're doing cursive, but you're doing it grandma style, you know? Mew. Mew. So 68% of the data is going to be between 68%, because 34 makes 68. Okay, so this is the mean. This distance is called one standard deviation from the mean. So what do those words mean, standard and deviation? Yes. Yeah, what does the word deviate mean if you're outside of math class? Like how far you go off of something. Like if you're deviating from the path, you're deviating from how you were raised or something. Deviate means like you're going off of like normal. Standard is what we use to describe like regular, right? So standard deviation is saying how far you're doing one distance, whatever that means, of deviating off of the average. Does that make sense? Okay. So if you deviate, this is mu minus 1 standard deviation. Now this is a...
What is that?
It's an O. It's like a cursive O basically, but I can't remember what that Greek letter is. Anyone remember? It's not mu. I should have looked that. I'll look that up. I'll find it and I'll look it up. Okay, so this is, and that should be plus. Sorry. I got thrown off because I couldn't remember it. So this is one standard deviation above average. And then this one over here is one standard deviation below average. So 68% of the whole population would be within one standard deviation of average. So above average or below average, they'd be within one standard deviation. Does that make sense? Okay. Now, if I do the average minus 2 standard deviations or the average plus 2 standard deviations, That's going to be 34%, 34%, 13.5%, 13.5%. So if I add all of those up, what do I get? 95%. So 95% of people would fall within 2 standard deviations. So we would say anyone within this is kind of like the usual. We wouldn't expect people to be in those outer sides. We would say most of the people, 95% of people are going to fall within that. That's pretty usual. Anything outside of that, we're going to be like, yeah, that's unusual if somebody's that far away. Okay, so then we're going to say 3 standard deviations. So if I have 2.35% plus 13.5 plus 34 plus 34 plus 13.5 plus 2.35. This would be not 100. 97.5%. Because, no, sorry. 99.5. Sorry. Okay. Whew. All right. So that last 0.15% in theory never happens. It just like trails off forever. These are like the people who earn 104% on a test. Like, how are you even real? No offense, Thomas. All right.
Thomas is not real.
All right, so what we just drew, the numbers that we just drew saying it's within 1 standard deviation, 2 standard deviations, 3, that is called the empirical rule. So this is the empirical rule. Okay, and that just states that on a normal curve, 68% of data is going to be within 1 standard deviation, 95% is going to be within 2 standard deviations, and 99.7% is going to be within 3 standard deviations. Make sense? Yeah, and then above that, you're talking weirdos. All right. Now we're going to go ahead and get some practice in. No, we're going to try to do some more, actually. Okay, so we're going to go ahead and label this. They say the average score on an exam was 82, so we're going to put an 82 right there in the middle, with a standard deviation of 5. So what is 82 plus 5? Plus another 5. Plus another 5. Okay. 82 minus 5. Minus 5. Minus 5. Okay. So I like to label my percents, maybe not for every single problem, but at least on the page so I can keep looking back at it. Okay. So the probability that someone scored between a 77 and an 87 is what? 68%. 68%. So if they scored between there and there, they are within 68% of the population that took that midterm. So 68%. Okay? What if they scored between 82 and 87?
34. Oh my goodness.
34%. Okay. 72 and 87%. 81.5. I'm going to go with, hold on. No, 81.5 is right. Okay. What? So 72 to 87 would be right there. Okay. Higher than 92. 2.5. Okay. A score less than 77. 16%. Okay. Now I'm gonna explain. Have you guys ever heard when they talk about babies and like their height? When they talk about babies and like their height and their weight and stuff, they say they were in like the 90th percentile. Do you know what that means? Yeah. It means that there's a bell curve with weight, and if they're in the 90th percentile, they're up here. It means they weigh more than 90% of babies. Okay? So if your score is, listen carefully, if your score is 77, then 77 cuts off right there, then you are in the 16th percentile. Okay? Now let's check out. If your score was 92, let's look at this. 0.15, 2.35, 13.5, 34, 34, 13.5. So if you scored a 92, you are in the 97.5th percentile. Does that make sense? If you scored an 82, you are in the 50th percentile. So that's how the percentiles work. They're based on the bell curve. Does that make sense? Okay. Let's look at the next one. These assignments reference SAT scores and ACT scores. Don't get excited. The numbers don't mean anything anymore because this is before the SAT and the ACT numbers changed. So don't look at this assignment and go, oh, that's probably pretty accurate. It's accurate based off old standards, not the current ones. Make sense? Okay. Yeah, don't be like, well, Miss Rice's math worksheet said this, because Miss Rice's math worksheets are old. Okay? All right. All right, so 490, a deviation of 100. Okay, and at this point, you're probably going to start working ahead because these are pretty easy. Yeah? Is that where we're at? Yeah? Just ready, set, go? Ready, set, go.
Like, I gotta wait.
Okay. All right. The average heights of American young adults are 68.5 inches for men and 65.5 inches for women, with a standard deviation of 2.7 inches and 2.5 inches. Most of us don't think of our heights in terms of feet like that, right? So if you want to convert it into feet and inches like we would normally do, this is a nifty little trick. So we do 68.5 divided by 12, right? Okay, go ahead and hit the math button and turn it into a fraction. Okay, this is going to be not great since this is out of 24. I'm going to go ahead and just say 69 divided by 12, and we'll fix it in a second. Well, no, it's okay. I'm just trying to, so if you do, this will take something that's an improper fraction and turn it into a mixed number for you, so you don't have to do that math by yourself. So that's 5 feet and 3/4 of a foot, and 3/4 of a foot would be 9 inches. 9 out of 12. So that means that 68.5 would be 8.5. So 5 feet, 8.5 inches is apparently average for young males, such as yourselves. I don't know if I'd agree with that. Maybe that would be average, actually. Okay. And then girls would be 65.5 inches. All right. So it says, Alexis Alexis is 3 standard deviations above the average height. Is she a typical height or an unusual height? Unusual, because she's 3 standard deviations. So if you can picture that normal, that bell curve, she'd be on like the 99th percentile. She'd be like way up at the top. Okay, so to figure out her height, we're going to say 65.5 plus, and how much are we going to add? Yeah, we're going to say 3 standard deviations, so 3 times 2.5, because 2.5 is 1 standard deviation for girls. Okay, so she would be 73 inches. You don't have to do this every time. I'm just going to write it in an answer that makes more sense. She is 6 foot and 1 inch out of 12. She's 6'1". That's pretty tall, right? But we said that was unusually tall, right? Does that fit? That's unusually tall? Yeah, that's pretty tall. All right, Marvin is 2.1 standard deviations above average height. How tall is he? So we would do 68.5 plus what?
2.1 times 2.7.
Okay. So he is 6 foot 2.17 inches. Okay. Miguel is 74 inches tall. Yeah, nose goes. Who wants to answer that? All right. Shh. So if we want to know how many standard deviations extra tall he is, we're going to do the average. So 68.5 minus 74. So first we just want to know how much taller he is than average. Actually, I should have done it. I'll do 74 minus 68.5. Okay. So he is 5.5 inches above average, and then to figure out how many standard deviations that is, we would divide by 2.7. Yeah. So it's 2.037 standard deviations.
Could you just replace the word standard deviation with symbol mu?
So can you take 5.5?
No, it's not mu, it's that little O thing. Mu is average. So you could say this, but that's weird. Okay. Deja is 62 inches tall. How many standard deviations below average is she? So we're going to say 62 minus 65.5. That's negative 3.5. Divided by 2.5. So she is 1.4 below. Yeah. Yeah, so you could say negative 1.4 standard deviations, or you could say 1.4 standard deviations below. Yeah. Stretch or question? Stretch. Okay. Steve is 71 inches tall. Mary is 68 inches tall. Which one is taller relative to the average for their gender? How could we figure it out? Yeah, find how much they deviate from normal. Whoever deviates the most from normal is more tall according to their gender. Okay, so for Steve, we're going to say 71 minus 68.5. Okay, and for Mary, we're going to say 68 minus 65.5.
So do we get that answer and divide it by their deviation thing?
Yeah, so this is 2.5 divided by 2.7. So he is 2.5 inches taller than normal, and the standard deviation was 2.7, and we can figure out what that decimal is. And 68 minus 65.5 is 2.5. Yeah, so if you look at that, they're both 2.5 inches taller than normal, but... Yeah, so this is slightly less than 1. This is 1 exactly. So relative to their gender, Mary's considered to be more tall than Steve. Does that make sense? Yeah. Okay. Now, this thing that we've been doing where we've been saying how many standard deviations, that's called a z-score. So we've already done it. That's what these notes are about. So a z-score is the number of standard deviations below or above average. So if the z-score is negative, then it's below average. If the z-score is positive, it's above average. So when we looked here, we had 2 different types of data we were comparing, but we knew that since her z-score was 1 and Steve's z-score was a decimal less than 1, we knew that her z-score was higher, which meant she was proportionally taller for her gender. Does that make sense? So z-scores are just a nice way to compare data if your data is based on 2 different things. Like if you're trying to say who's smarter and one person's math class is out of a certain number of points and the other person's math class is graded a different way, then you just compare those 2 math classes based on average. And whoever's the most better than average would be the one that you would say is quote-unquote smarter.
Press the thing. That's about it. Inside where the phone goes.
All right. So the formula, you don't have anything to take with you? Did they? Okay. Okay. Bye. All right. So the formula for z-score, think about what we did with each of these. What's the formula?
Probably number divided by average.
Wait, divided by average?
Number minus average.
Okay.
Divided, put that parentheses, divided by standard deviation.
Yeah. So we're going to say x is the number that we have. That's the thing that we're talking about. Minus the average divided by standard deviation. Okay. So you could say the value we have minus the mean or the average divided by standard deviation if you need the words in there. Do you know what that means? Mu.
That's just how we write my
Like the Pokemon.
Okay. So here's an example problem. We have 3 different athletes competing in some track events. You have competitor A, B, and C. They compete in the 100-meter dash, the shot put, and the long jump. And we have to figure out who wins overall. So if you look at the 100-meter dash, who won that? Person B, you want to run faster. Okay. So first, and now we know who the athletes are. First, second, third. Okay. Do we know what a shot put is?
Yes.
It's a metal ball that no, that's a hammer throw. Metal ball that you throw like this. Yep. All right. Do we want to throw less distance or more distance? More. Okay, so who won? So first, second, third, okay? And then with the long jump, do we want longer distances or shorter? Longer. Oh, goodness. Okay. So if we look at this, can you guys tell who won? They all had a first, second, and third.
Looks like some communism stuff.
All right, I need you guys to take it down a notch so you don't have more homework this weekend. Okay. I have to be able to get through the notes. All right, so everybody has a first, second, and third place. So that means that we need to figure out who was the best who was like better than average more often. Does that make sense? So we could figure out if we can find their z-scores, we can say, okay, they might have each gotten first, second, and third, but this person did way better when they got first. Or this person did way worse when they got third. Does that make sense? Okay, so what we're going to do is we're going to find the z-scores for each of the events. And then we can add them all up and see who did the best. Okay, so it says that the average for the 100-meter dash is 10 seconds. So we're going to say their score minus 10 divided by 0.2. And if you don't want to have to plug that in 2 steps, then you can do alpha y equals. So 10.1 minus 10 divided by 0.2. Now, this one is an interesting z-score because it's kind of opposite of what it should be, and that a score of 10.1 seconds is actually worse than average, right? It's a little bit slower than average, and the z-score makes it look like it's a good thing, but we know it wasn't a good thing to be slower than average. So even though I'm going to go ahead and write on my notes positive 0.5, and then I'm going to cross it out and put negative 0.5, because we wanted it to be slow. So this was like a bad z-score. It should be counting against them because they're a little bit worse than average. Okay, and then we're going to go ahead and do 9.9 minus 10. Standard deviation. Got it from the table. So we got negative 0.5, but we're going to make that a positive because we know they were a little bit faster than average, which was a good thing. It was just on the other side, right?
You can just assume, based by looking at the other ones, it's 1.5 for C, right? Based on.
I think so. Mental math is not always my strong suit.
Yes.
But it's going to be negative, right, because they're slower than average. Okay, so those are the z-scores we came up with. Only for that one because we want a lower number is actually better for you. So the way I was thinking of it is this is actually slower than average, which is not a good thing, and so that's why I made it a negative z-score, because usually a negative z-score is not what you want. Okay. All right, for the next one, we have the shot put. The average was 60 feet, and you can deviate from that by 3 feet. So for this person, we've got 66 minus 60 divided by 3.
So that would be 2.
Do any of you guys do the shot put, know anything about the shot put? You throw a ball. Has anyone ever watched the event? 60 feet is incredible. That is so far. Yes. If a student is throwing 60 feet in high school, they are like winning every meet. So average is probably closer to like 42. Yeah, to put it in perspective. All right, so 66 minus 60 divided by 3 is 2. 60 minus 60 divided by 3. Spot on, just average. 63 minus 60 divided by 3. Okay. All right, and then the last one, we've got 26 feet minus 26 feet divided by half a foot. See what I did there? It says 6, but it doesn't mean feet. It means inches. That's 0.5 feet. Okay? Oh, they switched units on us. Okay. 27 minus 26 divided by 0.5. So this one's 0, right? Okay. So 27 minus 26, that's 1.
So it would be 2.
1 divided by 1/2 is 2. Okay. 27 feet in 3 inches. So 27.25 minus 26 divided by 0.5.
That'd be 2.5.
Okay, so let's go ahead and look at all these z-scores. So what was person A's overall z-score?
1.5.
1.5. Okay, do we see how we're doing with that? Okay.
2.5 for B.
2.5 for B.
So 3.5 minus 1.5, so that's 2, so it'd be...
Okay, so person B, even though they all had a first, second, and third place, even though they all had like moments where maybe they did above average, below average, whatever, the person who did the best when you compare is person B.
Would you like add them?
That's what I did, is we added up all the Z-scores to see. Yeah.
Is that what they're doing, like, competitions?
I don't know. Honestly, I don't know if they'd be like...
Usually it's not. Usually those type of splits, it's team picks.
Well, yeah, it would be the team, and they would, the only time they would compare one athlete to another is if they did, like, heptathlon for women or decathlon for men. And I think it would be very rare, because what they normally do, like, with the shot put, you have 3 throws, and then if you get to finals, you get 3 more throws, and they look at, like, your farthest throw is what gets you your place, and if 2 people tie for first, then they look at your second longest throw, and that, so you would have to tie 6 throws, and that would not happen, yeah. I did the shot put.
Okay. I think so.
Ta-da! All right, person B. Flip the page over. All right, the mean score on the SAT is 1,500. Again, this is old data. Don't listen to this. With a standard deviation of 240. The ACT has a mean score of 21 with a standard deviation of 6. If Bobby scored a 1740 on the SAT and Kathy scored a 30 on the ACT, who did better? Okay, so what do we need to do? So Bobby, what should we do? Okay, so 1740 minus 1,500 divided by 240. Okay, and then Kathy is going to be... Kathy's going to be... Kathy's going to be... Kathy's going to be...
38 minus 21.
Okay. So this is 240 over 240, which is 1. So he did pretty good. 9 divided by 6 is... Okay, so who did better? Kathy, you're a winner, Kathy. All right. Next, we have Peter, who scored a 1380. Okay, all right. And Kelly, who scored a 15. All right, so Peter scored a 1380, so we're going to say 1380 minus 1,500.
Wow, you did cool.
And Kelly... So Peter got -1/2. Kelly got -1. Yeah. So when we're talking positive Z-scores, when you want to be a number that's above the average, then you want a bigger number. But when we're talking negative Z-scores, I definitely want to be below average if I'm talking about running speed. I want to be below average if I'm talking about swimming speed. I want to be below average if I'm talking about how much debt I have. But when I'm talking about SAT scores, I probably want to be above average, right? So Peter wins. All right. All right. IQ scores. The mean IQ score is 100 with a standard deviation of 16. Albert Einstein reportedly had an IQ score of 160. Whew. Okay, they want to know what percentile his IQ score was, so what we're going to do is we're going to draw that normal distribution, and we're going to figure out how many standard deviations he is above average, because that'll give us an idea of where he fell on the normal distribution. So if we do 100, sorry, not 100, we start with his, so we do 160. Because that's the value of his, minus the average, divided by standard deviation.
And that equals 160.
Okay.
So it's almost 4 deviations above average.
Okay, so he was between 3 and 4, closer to 4. So this is 34%, 13.5%, 2.35%. So this is 1, 2, 3 standard deviations, right? And that fourth standard deviation, that's the one where like all of them, kind of 4th, 5th, 6th, 7th, they're all in that little area, and that's the 0.15%. So that means he was in the 99.85. He was above the 99.85th percentile.
He's almost 4, so he's like very unusual.
So that means his score was pretty unusual. Because it's interesting, I want you guys to get out your phones and Google who has the highest IQ. So this is not a trap. So look up on your phones, Google who has the highest IQ. Yep.
It said it right there. Crazy things.
Yeah. It's a woman. Thank you. What was her IQ?
It was like 228.
228. Albert Schmalberg. Okay. And it's a woman. I leave you with that. Mic drop. That's why I want you to look it up. Yeah.